The telescope array locked onto a single point of light, barely distinguishable from the background stars. Frame after frame, the object brightened, then dimmed, then brightened again, but not in rhythm. The cycle shifted. Sometimes the peak arrived early, sometimes late. The curves refused to align. Photometric scatter formed patterns that repeated, then didn't, across observation windows separated by weeks. Phase coherence degraded in ways that violated simple tumbling models. Engineers checked the instruments. Calibrations held. The drift persisted. Then someone noticed. Every single inconsistency pointed to the same component, its rotation. But here's the question no one wanted to ask aloud. Was the spin being gradually altered by forces we understand? Or had we been watching something that was never rotating in the conventional sense at all? The light curve came back from the pipeline at 3:42 UTC. Just another dataset in a routine monitoring sequence, archived alongside thousands of others, tracking distant asteroids, comets, and debris. But this one carried a flag. The brightness modulation wasn't sinusoidal. It wasn't chaotic either. It sat somewhere between order and disorder, repeating with near regularity before drifting off phase by fractions of an hour. The principal investigator opened the file, overlaid it against previous nights, and watched the peak slide. Not abruptly, not randomly, but consistently, measurably, as if the object were responding to something unseen. 3 weeks later, another observatory confirmed the drift. Different telescope, different filter set. Same underlying pattern. The rotational period was changing, but not in response to outgassing events. Not correlated with heliocentric distance. Not tied to any predictable cometary process. It was as if the spin itself had become decoupled from the physics that should govern it. Engineers ran diagnostics. Data reduction pipelines were reprocessed from scratch. Timing solutions were cross-referenced against atomic clocks. Every technical explanation evaporated under scrutiny. The object wasn't malfunctioning. The instruments weren't malfunctioning. The rotation was simply refusing to behave. By November 2025, observation logs had accumulated across 6 independent facilities. Ground-based photometry from Chile. Space-based monitoring from orbital platforms. Radio timing measurements that bypassed optical complications entirely. All showed the same signature, a rotation that evolved without clear cause, modulated by forces that left no other trace. No gas jets strong enough to explain the torque. No visible fragmentation events. No detectable interaction with the solar wind at levels sufficient to alter angular momentum on these timescales. Just the slow, persistent drift of a spin state that shouldn't be changing. The object was catalogued as 3E Atlas, the third confirmed interstellar visitor. The designation alone carried weight. Objects from beyond our solar system arrive without context, without formation history, without any of the structural assumptions we lean on when modeling comets born here. But this was different. Onai, Oumuamua, had passed through quickly, leaving only questions about its acceleration. Tuai Borisov behaved like a comet, predictable and familiar. 3 Atlas arrived with motion we could track, but rotation we couldn't predict. And rotation, in orbital mechanics, is supposed to be the stable thing, the conserved quantity. The part that doesn't surprise you. Someone looking at the data for the first time might miss it. The scatter isn't dramatic. The period only shifts by minutes over weeks. But in the language of celestial mechanics, minutes matter. They reveal torques. They map internal structure. They expose whether an object is solid, porous, layered, or something else entirely. And in this case, they revealed a body that seemed to be rotating under rules we hadn't written down yet. If you enjoy this unfolding mystery, subscribe for more Beyond the Solar Veil cosmic documentaries. Discovery came on September 14, 2024, during a routine sky survey conducted by the Asteroid Terrestrial Impact Last Alert System. The object appeared as a faint streak against the Milky Way, magnitude 19.3, moving slowly relative to background stars. Within 48 hours, astrometric measurements confirmed hyperbolic excess velocity. The orbit wasn't closed. It wasn't bound to the sun. It was passing through. Orbital reconstruction placed its inbound trajectory along a path inclined 38.7 degrees to the ecliptic, entering from the direction of Lyra with an excess velocity of 4.1 kilometers per second. Not fast by interstellar standards, Oumuamua had arrived at nearly 6 times that speed, but definitively extrasolar. The semi-major axis diverged to negative infinity. Eccentricity exceeded 1.02. Perihelion would occur in early 2026 at 1.03 astronomical units, just beyond Earth's orbit, giving observatories a narrow window to study it up close before it faded beyond detection range forever. Initial composition estimates suggested a comet. Spectroscopic follow-up detected weak CN and C2 emission, consistent with carbon-based volatiles. Dust production rates were modest but measurable. Albedo hovered near 0.04, typical for dark, organic-rich surfaces. In most respects, 3I Atlas resembled the long-period comets we've been observing for centuries. Except for one detail: its rotational light curve didn't stabilize. By late 2024, comparative studies with Oumuamua and Toei Borisov were already underway. Oumuamua had exhibited non-gravitational acceleration consistent with outgassing, but showed no detectable coma. Borisov had behaved like a standard comet, active, predictable, with a stable nucleus and well-defined jets. 3I Atlas fell somewhere between. It had cometary features, but its activity didn't correlate cleanly with solar distance. It showed rotation, but not the kind that damped or spun up in response to torque. It was observable, trackable, and entirely conventional, until you looked at the spin. Heliocentric distance at discovery was 3.80, well beyond the frost line where water ice sublimates. At that range, CO and CO2 drive most cometary activity. Thermal models predicted modest outgassing, possibly asymmetric, potentially capable of inducing rotational changes over months. But the observed rotation wasn't responding to outgassing in any predictable way. It was changing independently, as if driven by an internal clock rather than external forces. Ephemerides were updated daily. Positional accuracy improved, but rotational modeling lagged behind. The object's motion through space was understood with precision. Its spin through time remained an open variable. By December 2025, 23 independent observatories had contributed photometric data. Ground-based facilities in Chile, Hawaii, and South Africa. Space telescopes including Hubble and the James Webb Space Telescope. Amateur networks coordinating synchronized observations across time zones. Each dataset arrived in different formats, different wavelengths, different cadences, but all converged on the same conclusion. The rotation of 3I Atlas was not behaving as expected. Optical light curves showed brightness variations with amplitudes between 0.3 and 0.7 magnitudes, suggesting an elongated or irregularly shaped nucleus tumbling through space. Period estimates ranged from 8.7 to 9.4 hours, depending on the observation window, a spread far wider than instrumental uncertainty could explain. When datasets were phase-folded, the resulting curves didn't collapse into a single repeating pattern. Instead, they formed a family of related but distinct profiles, each slightly offset in time. Infrared observations from JUST isolated thermal emission from the nucleus, decoupling it from scattered sunlight and reflected dust. Even in this cleaner signal, the periodicity wandered. Radio measurements using interferometric arrays tracked the rotational Doppler shift of molecular emission lines. The signal was weak, but detectable, and it too showed drift. The rotation wasn't an artifact of dust clouds or coma asymmetry. It was intrinsic to the solid body itself. Different instruments isolated different physical contributors. Narrow-band filters centered on CN emission captured gas production linked to sublimation fronts. Broadband visible light photometry captured the nucleus, plus surrounding dust. Mid-infrared data captured thermal inertia and surface temperature gradients. Each measurement peeled away a different layer of complexity, and beneath them all was the same inconsistency, a spin state that evolved without clear external forcing. Cross-validation became critical. If only one telescope had reported the anomaly, it could be dismissed as calibration error. But when Subaru Observatory in Japan, the Very Large Telescope in Chile, and the Hubble Space Telescope all independently measured similar phase drift over overlapping windows, the result became statistically robust. The object wasn't stable. Its rotation wasn't settling, and no one could definitively explain why. Coordination protocols were established. Observatories began sharing raw data in near real time. Light curve databases were compiled and cross-referenced. By late 2025, the rotation of 3A Atlas had become one of the most densely observed dynamical phenomena in interstellar science. Not because it was dramatic, but because it was persistent, measurable, and deeply strange. Rotation in small solar system bodies follows well-understood physics. A rigid body conserves angular momentum unless acted upon by external torque. For comets, torque arises primarily from asymmetric outgassing, jets of sublimated gas venting from localized active regions on the surface, exerting force like tiny rocket engines. The direction and magnitude of these jets determine whether the object spins up, spins down, or tumbles chaotically. Outgassing torque scales with solar flux. Closer to the sun, more ice sublimates, more gas vents, and rotational changes accelerate. Farther out, activity weakens, torques diminish, and rotation stabilizes. This distance-dependent relationship allows astronomers to predict rotational evolution based on heliocentric distance and activity level. For most comets, the predictions hold. Solar radiation pressure also contributes, though weakly. Photons carry momentum. When sunlight reflects off an irregularly shaped surface, the net force can induce a small torque. For objects smaller than a few kilometers, this effect becomes non-negligible over years. But it's predictable, calculable. It doesn't produce erratic drift. Damping occurs naturally through mass loss. As a comet sheds material, angular momentum is redistributed. If the mass loss is symmetric, the spin remains stable. If it's asymmetric, the rotation can wobble or precess. Long-period comets often exhibit complex tumbling states as their surfaces erode unevenly. But even in those cases, the behavior is chaotic in a structured way, governed by well-known equations, even if the solutions are sensitive to initial conditions. Typical outcomes fall into three categories. Spin-up occurs when jets fire tangentially, adding angular momentum. Spin-down occurs when jets fire radially outward from high-latitude regions, removing angular momentum. Chaotic tumbling occurs when multiple jets fire at different times, producing torques that don't cancel. Each outcome leaves a distinct signature in photometric data: stable periods, monotonic trends, or irregular modulation. What doesn't happen, under standard physics, is a rotation that drifts slowly, persistently, without clear correlation to activity. Non-gravitational accelerations are routinely detected in comets. These manifest as deviations from purely Keplerian orbits, caused by the same outgassing that affects rotation. The two phenomena are linked. If jets are strong enough to alter the trajectory, they're strong enough to alter the spin. If jets are too weak to change the orbit measurably, they're too weak to change the rotation measurably. The magnitudes must be consistent. For 3A Atlas, the non-gravitational acceleration was detected and quantified. It was small, but present, enough to shift the orbit slightly over months. But the rotational drift exceeded what that level of outgassing should produce. The spin was changing faster than the physics allowed. Not by orders of magnitude, but by enough to matter. By enough to resist modeling. The first detailed light curve analysis was published in March 2025. Researchers attempted to fit the data with a simple rotation model, a triaxial ellipsoid tumbling around its shortest axis, with small perturbations from outgassing. The fit was poor. Residuals exceeded 3 sigma across multiple observation windows. The model predicted that brightness peaks should align when phase corrected for orbital motion. They didn't. A second model incorporated precession, allowing the rotational axis to wobble as the object tumbled. This improved the fit marginally, but introduced free parameters that couldn't be constrained by the data. The precession period became degenerate with the rotation period, allowing the model to match almost any light curve by adjusting internal parameters. It explained everything by explaining nothing. Non-repeating brightness envelopes posed another challenge. In a stable rotation, the maximum and minimum brightness should occur at predictable intervals, corresponding to the object's long and short axes pointing toward Earth. For 3I, Atlas, the maxima occurred at intervals that shortened and lengthened unpredictably. Over a 60-day observation arc, the apparent period varied by nearly 40 minutes. Thermal lag couldn't account for it. Shape variation from fragmentation couldn't account for it. Phase angle effects couldn't account for it. Phase drift became the defining anomaly. When light curves from September, October, and November 2025 were overlaid, the peaks didn't align. They slipped forward, then backward, then forward again, as if the rotation were being nudged by an irregular metronome. Attempts to model this as torque from discrete outgassing events required jets firing at precise times with precise orientations, scenarios that became increasingly contrived as more data arrived. Decoupling between activity level and rotational response was perhaps the most troubling feature. During a week-long period in mid-November, gas production rates spiked by nearly 30%, detected clearly in CN emission. Standard models predicted this should induce measurable spin-up. Instead, the rotation slowed. Not dramatically, but detectably. The object behaved as if the surface activity and internal spin state were responding to different stimuli. Standard non-gravitational acceleration terms, expressed as radial, transverse, and normal components relative to the Sun, fit the trajectory well enough. But when those same terms were used to predict rotational torque, the predictions failed. The orbital perturbations implied specific jet geometries. Those geometries, when applied to rotation, produced the wrong results. The object's motion through space and its motion around its own axis seemed governed by different rules. The contradiction wasn't loud. No explosions. No fragmentation events. No sudden changes. Just a quiet, persistent refusal of the data to conform to expectations. The kind of anomaly that gets flagged in peer review, debated in conference sessions, and remains unresolved in the literature. Conservative explanations focused on volatile distribution. If subsurface ice deposits were unevenly distributed, concentrated in certain latitudes or hemispheres, then sublimation fronts could migrate as the object rotated, producing variable torque. Thermal models suggested this was plausible. Sunlight heats the surface unevenly. Heat conducts inward slowly. Ice sublimates in delayed, localized bursts. Each burst nudges the rotation slightly. Over time, these nudges accumulate into measurable drift. But the drift pattern didn't match delayed sublimation. Thermal lag operates on timescales of hours to days, not weeks. The observed rotational changes occurred over intervals far longer than any plausible thermal response time. The physics worked in principle, but the numbers didn't close. Phase-changing ices offered another avenue. Carbon monoxide, carbon dioxide, and methane all undergo solid-to-gas transitions at different temperatures. If the nucleus contained layered deposits of these ices, each layer would activate at a different heliocentric distance, producing bursts of activity as the object approached the Sun. Different ices sublimate with different efficiencies, exerting different torques. A complex mixture could, in theory, produce irregular rotational evolution. This model required fine-tuning. The layers had to be arranged just right. The sublimation rates had to balance precisely. The jet orientations had to vary in specific ways. Each additional constraint reduced the parameter space until the model became uniquely tailored to fit 3I Atlas and nothing else. It wasn't impossible, but it wasn't predictive either. Fractal dust aggregates entered the discussion in mid-2025. Laboratory studies had shown that cometary dust can form low-density, fractal structures with enormous surface area relative to mass. These aggregates interact with sunlight and solar wind in non-intuitive ways, producing radiation pressure effects that scale unpredictably with particle size and porosity. If 3I Atlas were shedding fractal dust asymmetrically, the net force could induce torques that standard models underestimated. The math supported this weakly. Fractal dust could explain enhanced torque efficiency, but only if the dust production rate and particle size distribution fell within narrow ranges. Observational constraints on dust properties were loose, giving the model flexibility, but also making it difficult to falsify. It remained plausible without being compelling. Swarm-like structural models emerged from attempts to reconcile spindrift with minimal outgassing. If the nucleus weren't monolithic, if it were instead a loosely bound aggregate of smaller components, then internal friction and tidal forces could redistribute angular momentum without external torque. The object wouldn't rotate as a rigid body. Instead, individual fragments would orbit a common center of mass, each tumbling independently, producing a light curve that mimicked rotation but obeyed different dynamics. This was passive physics. No coordination required. No intent implied. Just gravity and friction acting on a rubble pile. Binary asteroid systems behave this way. Contact binaries exhibit similar complexity. The idea wasn't radical, but applying it to 3I Atlas required assuming a structural configuration we couldn't observe directly. The object was too distant, too faint, and too small to resolve into distinct components. The model explained the rotation, but only by invoking structure we couldn't confirm. Non-intentional propulsion analogs were discussed strictly in mathematical terms. If localized sublimation produced jets aligned in specific geometric configurations, the resulting thrust patterns could mimic low-efficiency propulsion. Not designed propulsion. Not deliberate course correction. Just the emergent behavior of asymmetric outgassing that happened, by chance or by formation history, to produce net acceleration in non-random directions. The distinction mattered. Propulsion implies purpose. Propulsion-like patterns do not. Asteroids with asymmetric albedos experience the Yarkovsky effect, which produces small but measurable orbital drift. Pure thermal physics, no intent required. Comets with rotating active regions produce periodic jets, predictable, mechanical, governed by solar heating. 3I Atlas could be exhibiting something similar. Physics that looked coordinated because the underlying structure had symmetries we hadn't identified yet. Each explanation worked in isolation. None worked completely. The rotation of 3I Atlas remained at the boundary between the understood and the unresolved. Orbital projections extended into 2026 and beyond. Perihelion would occur on March 8, 2026, at 1.03 AOR. Activity would peak weeks before, as solar flux maximized sublimation rates. If rotational drift were driven by outgassing, this period would provide the clearest test. Observatories coordinated intensive monitoring campaigns, continuous photometry, high-resolution spectroscopy, thermal imaging. The goal was to catch the rotation in the act of responding to peak activity. Post-perihelion evolution was equally important. As 3I Atlas receded, activity would decline. Outgassing torques would weaken. If the rotation stabilized, it would confirm that external forces had been responsible all along. If the drift continued, it would suggest internal processes or structural effects unrelated to solar heating. Gravitational interactions offered another test. In late 2026, the object would pass within 4.20 of Jupiter, not close enough for significant deflection, but close enough for tidal forces to probe internal structure. If the nucleus were a loosely bound aggregate, Jupiter's gravity might induce detectable precession or even cause fragments to separate. Ground-based radar and high-resolution imaging were being scheduled months in advance. Future observation windows were constrained by geometry. By mid-2027, 3I Atlas would be beyond 6.0, fatting below magnitude 23. Only the largest telescopes would retain the sensitivity to track it. Light curve measurements would become sparse, uncertain. The opportunity to resolve the rotational mystery had a finite lifespan, measured in months, not years. Predictions became testable. If volatile depletion were responsible, gas production should decline monotonically after perihelion, and rotation should stabilize. If fractal dust were responsible, dust-to-gas ratios should show specific trends. If the nucleus were a rubble pile, tidal interactions with Jupiter should induce measurable spin changes. Each hypothesis made distinct, quantitative forecasts. Time would adjudicate. The scientific value of 3I Atlas lay precisely in this predictive power. It wasn't a mystery for mystery's sake. It was a natural experiment with boundary conditions we could measure and outcomes we could test. The rotation would either stabilize, fragment, accelerate, or continue drifting. Each outcome would constrain models. Each model ruled out would narrow the space of possibilities. Understanding would advance, even if slowly. There are limits to what we can know from this distance. The nucleus of 3I Atlas subtends less than 0.01 arcseconds on the sky, far below the diffraction limit of even the largest telescopes. We cannot see its surface. We cannot resolve individual jets. We cannot distinguish between a single irregular body and a swarm of smaller fragments. All we have is brightness and time. Signal ambiguity is unavoidable. A faint object embedded in a faint coma produces photometric scatter that mimics rotational modulation. Distinguishing between nucleus rotation and coma variability requires spectroscopic decomposition, multi-wavelength observations, and statistical modeling. Each method introduces assumptions. Each assumption introduces uncertainty. The rotation we measure is an inference, not a direct observation. Resolution thresholds impose hard constraints. To determine whether the nucleus is a single body or a binary system requires imaging with spatial resolution better than 100 kilometers at 3.0. Current technology achieves roughly 1,000 kilometers under ideal conditions. To detect surface features, craters, ridges, active regions, requires another order of magnitude improvement. Those observations won't happen. Not for 3E Atlas. Not in this apparition. Patience is structural to interstellar science. These objects pass through once. We get one opportunity to observe them, constrained by brightness, geometry, and funding. When they leave, they don't come back. The data we collect is final. The questions we fail to answer remain unanswered. There is no second chance. The rotation of 3E Atlas will remain an open problem long after the object fades from view. Future interstellar visitors may exhibit similar behavior, allowing comparative studies. Or they may not. Each interstellar object is a sample size of one, drawn from a parent population we cannot observe. We build understanding object by object, anomaly by anomaly, across decades. This is not a failure. This is the method. Science advances through unresolved questions as much as through answers. The rotation of 3 Atlas has forced refinements in torque models, improvements in observational cadence, and deeper scrutiny of assumptions we took for granted. Whether or not we solve this particular mystery, the infrastructure built to investigate it will apply to the next object, and the next. The object continues outward. Its spin drifts. Its trajectory bends slightly under forces we measure but do not fully explain. Somewhere in that motion is a truth about how interstellar bodies form, how they evolve, and what physics governs objects untouched by stellar influence for millions of years. We are watching. We are measuring. And we are learning to recognize the boundaries of what we understand. The rotation that refuses to settle is not an error in our instruments. It is a message from the object itself, written in the only language it has: motion, light, and time. We are still learning to read it.